Welcome to the second module of the compiler design course, where we talked about compiler phases last class. And in this module, we are going to talk about the compiler phases with reference to an example, and we will also talk about the tools that are available for the various phases of the compiler. The objective here of this course, of course, it's to learn an example on the process that happens in the various phases of the compiler, and also the tools available for the compiler phases, because constructing a compiler from scratch is going to be very tedious. Therefore, what normally happens is you will try to get the available tools and then try to integrate that for a particular language, and then use it as a reference to and try to build up on top of it and add some more modules, add some more functionality, add features which are necessary for a particular program input source program, and then depending upon the target program, again that could basically be modified. So, you are not going to design a compiler from scratch, you are trying to go through an existing tools which are available. So, let us just go through that before we look at the phases again as a quick recap. So, where the lexical phase, syntactic phase, semantic phase, intermediate code generation, all these four could be grouped into one pass. Optimization is one pass, and then code generation is going to be the next pass. Let us consider this example which is given in Aho Sethi Olman the textbook, which is position is equal to initial plus rate into 60. Now, this is what basically a user tries to code. So, in a C program or any Pascal program, this is a Pascal code because it says colon equal to for assignment. So, what any high level programming language will basically have such an instruction, and you have initial plus rate into 60. So, you have here your symbol table. The symbol table has simply now got the variables position, initial, rate, etc., and their corresponding attributes will basically be populated later. Now, I will also have here the data type associated with this in the symbol table, and this variable position is at location 1, variable position initial is at location 2, variable rate is at location 3. So, this is my attribute which I referred to in the first module. So, where we said every lexeme will have a name and an attribute. So, name is position, attribute is going to be the position in the symbol table, which is going to be 1 here. Now, if this is given to the lexical analyzer, what it does is it breaks this into tokens. So, it groups initial as one token, rate as one token, plus is another token, star is another token, 60 is another token. Same is the case with position and equal to. It is going to give, since these are variables, it is going to give identifier 1, identifier 2, identifier 3 to these variables. According to it, now it is going to be ID 1, ID 2 and ID 3. So, it simply breaks this into tokens, lexemes, okay, which is nothing but a sequence of characters, and assigns a token to every lexeme. Now, this is given to a parser, which is a syntax analyzer, okay, the second phase. The second phase, what it does is, using a grammar which is a context free grammar, it is going to construct a derivation tree, okay, otherwise called as a parse tree. Okay. So, I have here ID 1 colon equal to ID 2 plus ID 3 into 60. I am going to have ID 1 here. This is assigned a value which is computed by computing ID 3 into 60 first, then adding with that ID 2. So, I have ID 2 here, I have a plus here. With that, what will I add? I will add the multiplied value of ID 3 into 60. So, this is what it basically constructs. As of now, it does not understand what is happening here, how it should compute, but simply validates whether this statement position is equal to initial plus rate into 60 is valid or invalid is what it is trying to check. Okay, it will basically check and put it here. The next phase is going to be the semantic process, where I said type checking happens here, coercion happens here. So, coercion, assuming that this is initial plus rate into 60. So, rate is typically rate of interest is what this variable talks about. So, 60 is getting converted to a floating point number. Okay. So, it does a coercion here, where it converts into real of 60. It is going to convert this into 60.0. So, that is what basically happens in the next phase, it also tells it that ID1 can be of type only floating point, because anyway it is doing a type conversion here. So, it is going to basically say that ID1 will be of type floating point, that will be also checked and put in your symbol table here. And then that is given to the code generation phase, which is the intermediate code generator, where how it does is it converts this into real. So, that happens first. Every interior node is typically assigned a temporary variable, okay, and every leaf node is going to be your user defined variable. So, here I have 60, interior node is into real of 60. So, this is an interior node. So, I say temp1 equal to into real of 60, and then I can say temp2 is equal to ID3 into temp1. So, this is temp2, the node corresponding to the star node, that is a multiplication of LHS and RHS, that is going to be your temp2, which is ID3 multiplied by temp1, okay, because this node corresponds to temp1, and temp3 will be ID2 plus temp2, okay. ID2 plus ID2 is LHS, RHS is going to be temp2, which is the star node, and that is this node which is temp1, and that gets assigned to ID1. So, ID1 is equal to temp3. So, this is what happens in the intermediate code, where I have basically at the most 3 addresses to work with. And then the code optimizer, okay, what it does is temp1 is equal to into real of 60, okay. It is a constant value. So, it is trying to put that right away here and then multiply this with ID3 and put it to temp1. Now, what am I doing here? I am computing ID2 plus temp2, putting it into temp3, and temp3 gets put into ID1. So, I am combining the last 2 instructions into one instruction, where temp3 and temp3 both are same here, okay. So, I will simply call this as ID1 is equal to ID2 plus temp1. So, I have done some optimization here. There are a lot of optimizations available, and we will go through with that as we move on to the next modules. And then finally, the code optimizer will give this output, and the code generator will basically take this as an input and then converts this into machine instructions. So, what am I saying here? ID3 into 60.0. So, I will use a register called as R2, where I am moving the value ID3 into R2, and then I am doing a multiplication of floating point, where I am multiplying the register content of R2 with hash 60 points. It's a immediate operand 60.0, okay. It's a floating point multiplication. I have specified that, multiply floating point, and then I do what? Move this floating point value into temp1, which is nothing but ID2. Yeah, I have it R2 here, and then I am going to move, I am going to next step. So, R2 has the product of ID3 and 60.0, and then I am moving here ID2 into R1, and then adding R2 and temp1. Temp1 is available in register R2 here. So, add F R2 comma R1 and move the result back into ID1. So, move F R1 comma ID1. So, this is my flow. So, the first phase basically puts it into tokens. So, I have given names to them, which is ID1, ID2, ID3, etc. The second phase constructs a syntax tree to validate whether the input sentence corresponds to any syntax tree it has basically got. Now, the syntax tree is basically constructed based upon a known context free grammar. So, for every programming construct you have a context free grammar. So, given a context free grammar, to check whether a sentence belongs to this grammar or not can be done by constructing a derivation tree, otherwise called as the parse tree. That is what it constructs here, and then once the parse tree is correct, it is going to basically do a type checking and also do type coercion. After that, it is going to convert this into an intermediate code representation, and finally optimize the intermediate code and then generate the final code on the optimized intermediate code based upon a set of instructions set available with it. Now, supposing somewhere it goes wrong, supposing I have a plus plus operand here as against a plus operand. A plus plus operand does not require it requires only one operand, right? It does not require 2 operands. A plus plus operator here, it is going to throw an error here, but it is not going to stop with the compilation. it is going to log that as an error. It will recover from the error with some assumption. Okay. So, the assumption normally the compiler makes is can be grouped into two kind of assumptions. The one is the panic mode of error recovery, other one is the phrase mode of error recovery. The panic mode of error recovery is very simple. It is trying to simply delete some characters till it finds a proper character that matches a particular grammar. So, in the phrase mode it adds some logic, it adds some rules, it adds some things as error information, etc. So, that is a different set altogether. So, it recovers from the error with some assumption, but it logs that statement as an error in the error handler. Okay. And it proceeds with the compilation. The error recovery, the error handler's job is to simply recover from error, so that the subsequent compiler phases can be going on, okay, and not to just correct the user error and then proceed with the compilation process assuming it is going to be correct. Okay. So, this is what happens in the compiler's phases. Let us just expand on this example. Position is a lexeme ID, lexeme mapped into a token ID comma 1, okay, where ID is an abstract symbol standing for identifier and 1 points to the symbol table entry for position. This is what I said, it is going to have a name and a attribute. The attribute is going to be 1 here because it is available at the first position in the symbol table, and ID is going to be the attribute because the compiler gives it as identifies position as identifier 1. The symbol table entry for an identifier holds information about the identifier such as its name and type. Okay. Other information are also possible to be put into your symbol table. We will move on as we will inform as we move on with the syllabus. And then equal to is a lexeme that is mapped into the token assignment operator. Since this token needs no attribute value, we have omitted the second component of the information, that is every lexeme has got two components, right, one is the name, other one is the attribute value. So, since this is going to be an operator, there is no attribute value available here. So, it simply has the assignment operator as the information. Same is the case with initial. Initial is a lexeme that is mapped into the token ID comma 2, where 2 points to the symbol table entry for initial. And plus is a lexeme, again it is going to be mapped into token plus. Rate is a lexeme mapped into the token ID comma 3, where 3 points to the symbol table entry for rate. Similarly, with this case of star and 60. Star is a lexeme that is mapped into the token star, which is indicating multiplication operation, and 60 is a lexeme that is mapped into the token 60, again does not require any symbol table entry here. After simply tokenizing, simply putting it as lexemes, you have the grammar, context free grammar for assignment expression, which is nothing but statement produces ID colon equal to E. Okay. LHS is simply an identifier, RHS will be an expression. The expression can be, of course, I have just given here expression involving multiplication, addition and parenthesization. So, where this E could be E plus T or T and T could be T star F or F produces parenthesis E close parenthesis or ID. So, this is what basically the grammar corresponds to, this is a subgrammar corresponding for an assignment expression, because I have not looked upon arrays here, I have not looked upon pointers here, I have not looked upon other operators here. So, therefore, this is just a small subset, subproduction set of a assignment expression grammar. So, for that particular grammar, this is going to be my corresponding derivation tree. Okay. So, here S produces ID colon equal to E, this is my S here, LHS is ID colon equal to, this is my expression here. This expression is expression plus T. This expression is nothing but T, which is nothing but F, which is nothing but a simple identifier initial. If you remember that, expression produces T, T in turn produces F, F in turn produces ID. So, in our example, expression here is nothing but E, this is the same E, okay. This E produces E plus T, this is T, T produces F, F produces initial. So, initial is my identifier here, again plus T. Now, this T is nothing but T star F, okay, T star F, where T again corresponds to F and then ID, ID is nothing but rate here, and this F corresponds to ID, where ID here is a constant. So, ID colon equal to E plus T, where this T is T star F. Okay. So, this is an unambiguous grammar. okay, E plus T and T star F. This is a unambiguous grammar of the expression grammar here. So, I am able to map this statement with my expression grammar available. Therefore, this statement is syntactically correct. Okay, that is what happens in the second phase of the compiler. So, this is what we just now saw, id comma 1, this is my lexeme, equal to id comma 2 plus id comma 3 into 60. So, the parse tree is constructed, the parse tree is correct, and the compiler proceeds to the next phase. If the parse tree is incorrect, on the other hand, what happens is this basically recovers from the error and then logs into the error handler for subsequent correction by the user. Now, this is what happens as the intermediate, as I just now said. T1 is equal to into float of 60, T2 is equal to ID3 into T1 and T3 is equal to ID2 plus T2 and ID1 equal to T3. This is what happens in the 4 steps of the code generation, similar to corresponding to this one. As I said, interior nodes are numbered T1, T2, T3. So, T1 is equal to this into 60, T2 is equal to ID into something, and finally, ID is equal to this one. So, with that you can optimize as we already said, okay, and then this is going to be my final code corresponding to generating. So, similar the example same example which I gave you earlier, the same thing is here given again for a better understanding. So, in the first 2 phases you normally have the lexical phase basically does the job of combining you based upon what is called as a regular expression for defining patterns, and the second phase uses a context free grammar for validating your syntax of every statement, and the third phase uses the type checking again based upon some for every grammar production you will have semantic rules to convert and do type checking, and the third phase and the fourth phase, the intermediate code generation phase, basically uses a lookup kind of scenario where if this is going to be my input, for every interior node create a new label and then it is going to create semantic rules. Again the semantic rules are created for every grammar production, and then the code generation phase uses this intermediate code and generate final code based upon the target instruction set. Now, after this example, let us just move on to the cousins of the compiler. The preprocessor, assembler, the loader, linker and the debugger all are basically called as the cousins of the compiler. So, we already said what is a preprocessor. Preprocessor is simply your hash define, your macros, all these are preprocessors. They are basically converted into the source language itself before compilation, and assembler is the compiler generally produces assembly code as we already know, and the assembler uses this to generate a relocatable machine code. Loader copies the code into memory for execution, it allocates storage, setting production bits, mapping virtual addresses, etc., and the linker handles relocation and resolves the symbol references. Now, debugger basically is a tool, is a utility used to identify and pinpoint errors in your source code. So, as I already said, the compiler is not constructed directly from scratch. The compiler is basically constructed based upon some available existing tools. Now, we have various tools available and we will just list here a few. The first one is the lexical analysis phase, a tool which is called as a scanner generator, whose input will typically be a source program and the output will basically be a sequence of lexemes. The task of reading characters from the source program and recognizing tokens or basic syntactic components are done by this based upon a list of reserved words. So, the lexical analyzer basically uses a list of keywords and reserved words, and it also has some patterns available. Based upon whatever pattern you specify, it compares with the list of reserved words and then generates lexemes accordingly. The lexer typically available is the lex, which is a short form of lexical analysis generator, or you can also have a version of lex called as flex, which is fast lexical analysis generator. These two, these are basically utility available as part of the Unix programming environment, where it is a rule based programming language. Lex is a tool, it is a rule based programming language, as against your structured or object oriented programming language. This is a rule based programming language. So, how it does basically is it has the definitions are within a pair of a double percentage. Okay. So, the first, it has got 3 sections. The first section basically is going to be specifying the declarations, what variables you want, etc., could be declared there. And in the second section you will have actions and rules. Okay. You will have actions and rules, that is, if this is going to be my action, what rule should I basically adopt. That is action in the sense that you will define a pattern as the LHS, the corresponding RHS will basically be a action on that pattern. Okay. So, this is what is a rule based programming language typically is expected to do. Supposing if I wanted to print from a sequence of from a string, if I wanted to print characters that begin with a K. So, I will define a pattern for this particular output which I want. For example, I want to start with K and then I can have any number of characters. So, my regular expression will be correspondingly K followed by any combinations of A to Z or A to Z, small and capitals can be mixed up. If that is my thing, I will do what? I will simply do a print of that particular pattern of that particular word. So, I will simply say okay, print this word, that is my action. So, I have a pattern and a corresponding action, that will be in the second section. The third section will basically be a simple C program main function and a return statement. So, what it does is it uses a Lex compiler. The Lex compiler, okay, this will basically be defined as a .l file, and a source program which is written in the language Lex, which will have a .l extension indicating for Lex. Okay. After a .l extension is available, this will run through a Lex compiler. The Lex compiler provides an output as lex.yy.c file, which is a .c file. Now, once I have a .c file in place, I can use a C compiler to run this to generate an output. Okay. So, the output will basically be whatever pattern I have specified and whatever action basically does basically perform for the particular pattern match. So, in our example, I said if it starts with a K, print that word. So, words starting with K alone will be printed, the rest of the words will basically be skipped. Okay. So, like that I normally define patterns to do whatever I want it to basically do. So, this is what is the first phase job. The second phase is nothing but the syntax analyzer, that we have a tool. The tool is called as a parser generator, and it basically produces an yes or no answer. Okay. This is also available as part of the Unix environment, where the tool is called as a YAC. YAC basically stands for yet another compiler. You have another tool called as Bison. All these both are actually parser generator, that is, given a particular grammar, again this has got 3 sections. The first section will basically be again between pair of percentage symbols. I will have here again the variable declarations and the grammar will be declared here, and the second part will basically be the action and the rules, and the third part will again be the simple main of your C language. Again this is going to have the input which is going to be a .y file, y stands for YAC, output will basically be a y.tab.c file, and this y.tab.c will be compiled by a C compiler to generate the executable. So, these two tools are going to serve as the first and the second phase of the compiler. Okay. So, you have other tool like Bison also, which is going to be a YAC, and both these are LALR parsers. We will see what is LALR parsers in the subsequent modules. Then the semantic analyzer, there is a tool which is called as the syntax directed translator, where the input is going to be a parse tree and the output will be the routines to generate intermediate code. It is going to just give you what routines are required to generate an intermediate code for a particular piece of input. The role of the semantic analyzer is to derive methods by which the structures constructed by the syntax analyzer may be evaluated or executed. So, there is one more tool here which is called as the syntax directed translator. You also have a type checker, where it is based upon two common tactics. The first one is to flatten out the semantic analyzer's parse tree. The second one is embed the semantic analyzers with the syntax analyzer, which is called as syntax directed translation. So, type checking basically happens by looking at only the leaf nodes and looking at just the intermediate node, interior node, and then evaluating what type checking is required, or you can also embed this along with the syntax analysis phase also. And then the next one is called as the intermediate code generator phase, which is another utility called as automatic code generators. Now, this is very important because code generators, we have so many algorithms, so many methodologies, because in code generation the primary concept or the primary problem is to get a register, because as we know, if you put it in a register, it is going to be resulting in faster execution, resulting in reduced instruction cost. So, we will tend to get put everything in a register and try to perform the operation, but there are no many registers available as there are variables. So, what we normally do is we will try to do an optimization on the registers. So, with all these in place and then trying to generate code, that will be a tedious task. So, what we normally do is we will try to resort to the automatic code generators, where it is going to have intermediate code rules, that is input will be an intermediate code generator, intermediate code which is already optimized also, and then you will have some algorithm to convert this into a intermediate representation. Now, this intermediate representation is different from your 3 address code representation. This representation is going to be catering to the necessity of the code generator algorithm, which is a template. Okay. Now, this template will be used by the code generator, and then it will generate, it has a set of rules. If this is my template, the corresponding code is this. If this is my template, the corresponding code is going to be something. Okay. So, what is our job? Our job is simply to convert the intermediate code, which is the 3 address code, into a representation which the code generator can basically understand. Okay. Then the task of the code generator is simply to traverse this tree, and it produces functionally equivalent object code. Okay. 3 address code is one type, and then output could be the final output also. Then on to the next tool, which is called as data flow engines, whose input will be an intermediate code, output will be the transformed code. Now, there is a simple thumb rule in code optimization, where we normally say if the cost of optimization is going to be more than the cost of generation, do not try to optimize. Okay. So, therefore, the intermediate code will be given as input to the optimizer. The optimizer tries to apply some basic optimization techniques like common sub expression elimination, dead code elimination, copy propagation, constant folding, algebraic simplification will be applied, and then it is going to generate final code, and this code is now going to be used by the code generator for creating assembly level code. So, you also have automatic code generators. The code generator can basically work either at the ICG level or at the final level. Okay. So, let us take this example 8 into x divided by 2. So, load a with x, multiply a comma 8 and divide a by a comma 2. Okay. So, this is just an example. So, that completes this module. So, what we have discussed in this module is we have basically taken an example and have seen how the various phases of the compiler basically puts this code into, breaks this code, understands it, analyzes it, and then converts into final assembly language. And then we also talked about the basic compiler construction tools like your Lex, your YAC, automatic code generators, data flow engines, and syntax directed translations, etc. There are of course other tools also available. One is called as the pretty printers, which is going to simply check whether the printing sequence is going to be correct or not. That is, it is trying to align, indent all your code beautifully and then show that this is what is your final code. That is called as pretty printers. So, we also have data flow engines to check whether the data flows from one module to the next module is going to be correct or incorrect. So, other tools are also available. I have just listed out what is necessary for definitely necessary for a compiler to be constructed. and then you normally integrate the tools and then modify the tools to suit your compiler needs. So, that is what we have talked about in this particular module. So, we will stop here and continue with the next module.